In part 2 of this module, we continue the discussion of manufacturing measurements, where we see that data from repeated measurements often vary. Distributions of that variation can be modeled and used to estimate the probability of measurements and our confidence that the measurements will occur over a specific range. The core problem we're trying to address with manufacturing measurement statistics is estimating the true value of a measured variable x prime. Our best estimate for the true value is the sample mean, x bar, plus or minus our uncertainty estimate u. We state this range with a percent probability p, or confidence. In our ball screw bearing example, we might estimate the true value as the sample mean of 1.98 millimeters, plus or minus the uncertainty 0.04 millimeters. Our estimate of uncertainty is at a 95% confidence. While computing the mean is rather straightforward, we need to learn how to estimate the uncertainty for a given probability. Probability deals with the concept that certain values of a variable may be measured more frequently relative to other values. The central value and those values scattered about it can be determined from the probability density of the measured variable. The frequency with which the measured variable assumes a particular value or interval of values is described by its probability density. Consider a sample of x shown in which consists of n individual measurements, xi, I equals 1 to 20, where each measurement is taken at random but under identical test operating conditions. The measured values of this variable are plotted as data points along a single axis shown. We can see a portion of the axis on which the data points tend to clump. This region contains the central value. Such behavior is typical of most engineering variables. We expect that the true mean value of the population of variable x is contained somewhere in this clump. The central tendency description of the variable x can be extended. Suppose we plot the data in a different way. The abscissa will be divided between the maximum and minimum measured values of x into k small intervals. Let the number of times nj that a measured value assumes a value between an interval be defined by x minus delta x is less than x plus delta x and be plotted on an ordinate. The resulting plot of n sub j versus x is called a histogram of the variable. The histogram is just another way of viewing both the tendency and the probability density of a variable. The ordinate can be non-dimensionalized as the frequency, fj equals n sub j over n, the total number of samples, converting the histogram into a frequency distribution. For small sample size n, the interval number k should be conveniently chosen with a good rule of thumb, such as n sub j greater than or equal to 5 for at least one interval. One suggestion for setting the minimum number of intervals k uses a correlation developed by the data from Bindent, which is k equals 1.87 times n minus 1 to the 0.4 power plus 1. As n becomes large, k approaches n to the 1/2, which works reasonably well at creating meaningful looking histograms to show the distribution of data. Here we see the histograms of our data with some additional features. On the left we see cumulative percentage as a line adding up 0 to 100% from left to right. On the right side we see a histogram with a different scale in the vertical direction. In this case, it's frequency as opposed to number of occurrences. The frequency is just the number of occurrences for a given bin divided by the total count. In this way, all of the bins add up to 1, or 100% probability, covering all of the values of our measured data. As the number of samples n goes to infinity, the probability density function p of the population of variable x is developed. In the limit of small changes, delta x goes to 0, p equals the limit, as delta x goes to 0, of n sub j over n, the number of samples, over 2 delta x. The probability density function is a statistical model of the population of a variable. It defines the probability that a variable might assume a particular value upon any individual measurement. It also describes the central tendency of the variable and its variation. The central tendency is the desired representative value that gives us the best estimate of the true mean value. The actual shape that the probability density function takes depends on the nature of the variable it represents and the circumstances surrounding the process in which the variable is involved. There are a number of standard distribution shapes that suggest how a variable could be distributed. Some common engineering examples are shown in the table here. The specific values of the variable and the width of the distribution depend on the actual process, but the overall shape of the plot will most likely fit one of these. Often, experimentally determined histograms are used to infer guidance on the most likely model for P, the probability density function. Of course, these aren't inclusive. The first distribution is the normal distribution. Most physical properties that are continuous or regular in time or space with variations due to random error fit the normal distribution, sometimes called the bell curve or Gaussian distribution, characterized by the mean and standard deviation. A related distribution is the log normal distribution, often used for failure or durability projections, events whose outcomes tend to be skewed towards the extremity of the distribution. You can have a rectangular or uniform process in which the likely outcomes fall in the range between the minimum A and the maximum value, occurring with equal probability, or you might have a triangular shaped distribution or a Poisson distribution for events randomly occurring in time or space. P refers to the probability of observing X events. Here lambda, the parameter, refers to X prime. Another common distribution is the binomial distribution, situations describing the number of occurrences N of a particular outcome during N independent tests where the probability of any outcome P is the same. Regardless of its probability density form, a variable that shows a central tendency can be described and quantified through its mean value and variance. In the absence of systematic errors, the population true mean value or central tendency of a random variable X is the continuous in time or space, and having a probability density function P is given by the parameter X prime equals a limit as t goes to infinity of 1 over t integrating from 0 to t of x sub t dt, which for any continuous random variable x is equivalent to x prime equals the integral from minus infinity to infinity of x times the probability density function p of x integrated over dx. If the measured variable is described by discrete data, the mean value of the measured variable xi, where I equals 1 to n, is given by x prime equals the limit as n goes to infinity of 1 over n of the sum of xi over n. Unfortunately, there's no way to apply manufacturing statistics correctly without having a little exposure to this kind of mathematical background. We try not to think of it as theoretical, but the reality is this and the next couple slides have a bit of calculus or integration. The key is not to be able to do that type of math, but to understand the concepts, as it'll lead to a better understanding of what statistics to use, what probabilities to use, and how to apply them to manufacturing problems. Physically, the width of the density function reflects the data variation. For a continuous random variable, the population true variance is given by sigma squared equals limit as t goes to infinity, 1 over t, the integral of 0 to t of x sub t minus x prime squared dt. This is equivalent to sigma squared equals the integral of minus infinity to infinity of x minus x prime squared times p of x, the probability density function, over dx. Or for discrete data, the population variance is given by sigma squared equals limit as n goes to infinity of 1 over n summed xi minus x prime, the deviation, squared. The population standard deviation sigma is a commonly used statistical parameter, and it's defined as the square root of the variance. Sigma equals square root of sigma squared. The fundamental difficulty in using these formal true population mean and variance equations is that we assume a knowledge of the values of the entire population of the variable. But what if the dataset represents only a finite portion of that population? Do these relationships change? Real dataset sizes may range from single values to a large finite number. In the next section, we'll begin to discuss interpretation of the behavior of an entire population of a variable with a connection between probability and statistics. Then we'll focus on trying to infer behavior of a population based on the statistics of finite data sets.